So example 18, recognizing a horizontal compression on a graph. We want to relate the function g of x to f of x in the figure 26. So here we have a function g and we have a function f. So the function f has an ordered pair of 6, 4. And then we can see what happens that this ordered pair now has become 2, 4. So the graph g of x looks like the graph f of x horizontally compressed. So because f of x ends at 6, 4 and g of x ends at 2, 4, we can see that the x values have been compressed by a factor of 1/3. Because 6 times 1/3 is going to give us an x value of 2, and the output remained the same. So we might also notice that g of 2 is equal to f of 6, and g of 1 is equal to f of 3. Either way, we can describe this relationship as g of x, which is equal to f of 3 times x. Meaning that if we go from this function to this function, we had to multiply 2 times 3 to get 6. So this is a horizontal compression by 1/3. So to relate g of x to f of x, we know that g of x has an ordered pair of 2, 3. We know that f of x was then 6, 4. So that means that in order to get 2, 4, we had to multiply 6 by a factor of 1/3, because 1/3 of 6 is 2. So that means g of x is going to equal f of 3 times x. So this 3 times that 2 gave us 6. Now notice that the coefficient needed for a horizontal stretch or compression is the reciprocal of the stretch or compression. So to stretch the graph horizontally by a scale factor of 4, we need a coefficient of 1/4 in our function, f of 1/4 of x. This means that the input values must be 4 times larger to produce the same result, requiring the input to be larger, causing the horizontal stretching. So if related to f of x to g of x, f of x gave us 6, 4. G of x gave us 2, 4. So that means we're taking 3 times 2 of 4, 6, 4. So f of x would equal g of 1/3 of x.